everyone, and welcome to episode 4 of Explaining Physics Concepts. We're looking at thermal physics, part 2, where I'll be explaining what is heat capacity, latent heat, fusion, vaporization, and then we're going to be doing a past paper question. And in our next video, we will be doing thermal physics just for ideal gases. So stay tuned for that as well. Now, I'm going to tell you something very common but very misunderstood, and you may know it, but I just want to reiterate it in this video because it's like sort of it forms the backbone of this entire chapter. Number one, that is temperature and state are mutually exclusive. What I mean by that is a change in temperature and a change in state cannot occur simultaneously. If there is a change in temperature, the state cannot change during that time. So you must have seen cooling curves and heating curves like this. And when here when the temperature remains constant, that is when there's a change in state, and here when the temperature keeps on increasing, the state does not change, it remains ice. And here this is where the melting starts occurring because the temperature is constant, so they cannot occur at the same time. Moving on, let's move on towards what do we mean by specific heat capacity. So in our last video we talked about how when there is a change in temperature, it's related to heat capacity or latent heat, heat capacity, and if there is a change in state, that is related to latent heat. So we're going to be looking at specific heat capacity. First, what do we mean by specific heat capacity? Let me quickly type this down. Okay, it is the amount of heat energy required. It is the amount of heat energy required, or you can say involved, to change the temperature of an object of mass 1 kg by 1 Kelvin. So you see there is only a change in temperature, and the reason why it's specific because it involves mass. So you're saying mass of 1 kilogram. If it was just heat capacity, you wouldn't have mentioned mass. Next up we have is specific latent heat. Okay, specific latent heat, it is the amount of heat energy required to change the state of an object, of mass. I have to mention mass because I'm doing specific latent heat without, I'm going to capitalize it because it's very important, without a change in temperature. So you're talking about change in state here, but you have to mention that there is no change in temperature while that is occurring. And then let's further break this down. We have specific latent heat of fusion, and we have specific latent heat of vaporization. Vaporization is again vapor gas. Fusion is when it comes to liquids. So what do we mean by specific latent heat of fusion? It is the amount of heat energy required. Let me just copy this. Amount of heat energy required involves to change the state of an object of mass 1 kilogram from solid. You just have to add from solid to liquid, or vice versa, without a change in temperature. And when you talk about specific latent heat, of vaporization, it will be the exact same thing of an object from liquid to gas or vice versa. That is all that you have to change. From liquid to gas without a change in temperature, and that is it. And now we're going to take a look at the formulas. Let's take a look, start off with specific heat capacity, and here it is. Okay, so you have specific heat capacity. You must have seen this formula, Q equals mc delta theta. That is literally it. But I'll say instead of Q we write E, but that is energy, and mc delta T, where m is the mass, C is the specific heat capacity, and delta T is the change in temperature. If I were to make this the subject, because this is the specific heat capacity, it will be E over m delta T, and so E is joules and m is kilogram and temperature is Kelvin. So this is the formula. And if you just have to take a look at only heat capacity, you just remove the m and you will get C equals E over delta T. And now for the latent heat, you have energy, then you have mass, and then you have L. L is the latent heat. It can be latent heat of fusion, or it can be latent heat of vaporization, depending on what is happening. Now I'm going to give you a very simple example of how to approach questions. Let's say, okay, let's say there is an ice on temperature of minus 13 degrees Celsius, and you have to convert it into 120 degrees Celsius steam. Now the reason why I'm doing this example is so that you can know what formula to use when, what are the series of steps that you need in order to reach from minus 13 degrees to 120 degrees. Now when you have minus 13 degree ice, first that minus 13 degree ice has to come to 0 degree ice, right? Minus 13 degree ice has to come to 0 degrees. So there is a change in temperature, so both of them are ice. Okay, both of them are ice, so there is no change in state. They are ice, but there is a change in temperature, so you have to do which formula? MC delta T. And then from 0 degree ice you go to 0 degree water, right? This is how melting occurs. Melting occurs, there is no change in temperature, but there is only a change in state. So 0 degree water. Now there is no change in temperature, there is a change in state, and change in state is only related to latent heat of fusion because it's melting. So you will use the formula MLF, latent heat of fusion. And then from 0 degree water you have to go to boiling, right? I have to go to steam, so I have to go to 100 degree. I have to break it step by step. You cannot go from 0 degree to 120 degree. You have to go to 100 degrees Celsius water, because first there will be a change in temperature and then there will be a change in state. So first there is a change in temperature, again I'll use MC delta T, and then I'll go to 100 degrees Celsius steam, because if you just bring in your mind the heating and cooling curve, you'll see first there's a change in temperature, and then once the temperature has changed, then there's a change in state, and now you will use MLV, and then from 100 degrees Celsius steam you will go to 120 degrees Celsius of steam. So now there is no change in state, there is only change in temperature, and you will use MC delta T, and that is how you have to approach questions whenever you see, just break them down. First there will be a change in temperature, then there will be a change in state, then there will be a change in temperature, then there will be change in state, and that is how you do it. So this is it for this part. Now I'll just move on towards the question. It's a very extremely old question, I would say, but I would say something that is very conceptual and would really help you understand. So the question is summer 2003, paper 4, question 2. I would definitely recommend doing this question by yourself as well. So the first part is, on figure 2.1, place a tick against those changes where the internal energy of the body is increasing. Internal energy is only related to the potential random distribution of potential energy and random distribution of kinetic energy. And it says water freezing at constant temperature. Okay, if there's constant temperature, that means the random distribution of kinetic energy is not changed, and it's freezing, it's coming together, so there's a decrease in the random distribution of potential energy because they're coming close together. This is not an answer. A stone falling, it does not match. Water evaporating, yes. And since there is constant temperature, you see how they're also mentioning water evaporating at constant temperature. There's a change in state, but there's no change in temperature. So yes, they are going far apart. That means the spaces between them is increasing. So yes, this will be an answer. There's an increase in internal energy. So third one. And stretching a wire at constant temperature, yes, fourth one as well. I wanted to do B part the most because I feel like very hard but very interesting. A jeweler wishes to harden a sample of pure gold by mixing it with some silver so that the mixture contains 5% silver by weight. The jeweler melts some pure gold and then adds the correct weight of silver. The initial temperature of the silver is 27 degrees Celsius. Use the data of figure 2.2 to calculate the initial temperature of the pure gold so that the final mixture is at the melting point of pure gold. And then they have given us a table where we have the melting point, specific heat capacity, and specific latent heat of fusion for gold and silver. Okay, a lot of information given to us, but we will break it down and make it very simple for us. Okay, first what I would like you to do is, I'll write gold here and then I'll write silver here. For gold, I'll use purple color, red color, let's use red. Now gold, you see how it says, now we have to just decide on whether we're going to use change in temperature formula or change in state formula. That is the key here. A jeweler wishes to harden a sample of pure gold by mixing it with some silver, and then the jeweler melts. So the gold is already melted. Since it's already melted and there is no change in state, which means there will be only, since it's already melted, and we just have to increase its temperature or decrease its temperature, whatever the question is asking. That means we have to use the formula MC delta T. That is what you have to determine. Since it's already melted, so you do not need latent heat of fusion. We only need to change its temperature. So what's its mass? Mass is given to us. Oh, mass is given to us. Another key here. The question says, mixing it with some silver so that the mixture contains 5% silver. If the mixture has, let's say you have a mixture here, and the mass of the mixture is M, and from that M, 0.05 M is silver, and the rest is gold, obviously, so 0.95. So I'll write 0.95 M times specific heat capacity is given to us, which is 129, times change in temperature. Now what do we have change in temperature? Change in temperature is the bigger value minus smaller value, and in this case, and we have to find out the final, calculate the initial temperature now. And the melting point is 1340 given to us. Okay, calculate the initial temperature so that the final mixture is at the melting point of pure gold. So that we have the final temperature, that is 1340. We have to find the initial temperature, and you, in your head you will be like, oh, we have to write 1340 minus initial temperature, but no, it's the opposite here, and that is the key here. Why? let me write I initial and then minus 1340. In order to bring this mixture to the melting point of the gold, the initial temperature should be great. Let me explain it through a graph. You have this, and here 300, 1240. 300 is the temperature of silver in Kelvin, 27 plus 273, and then you have 1340, and then I do not know the initial temperature now. For the silver, it goes from here, and then at 1240 it's the melting point, so there's no change in temperature, there's only change in state. And then for gold, this. Now for the gold, you have to melt it, so the initial temperature has to be greater than 1340 to bring it down to 1340. Right, that is why initial temperature is greater than 1340. I write bigger, minus 1340. I hope that made sense. So this is it that we need for gold. Now let's come to silver. In silver, it says mixing it with some silver so that the mixture contains 5% silver by weight. So it doesn't say it has melted the silver, that means it just adds the silver to it, so it's solid at first. Since it's solid at first, you start off by increasing its temperature. I've always mentioned first temperature increases, then there's a change in state. So 0.05 m, because 5% is silver, so 0.05 m times 235, because specific heat capacity, times, now what's the final temperature? The final temperature is the melting point of silver, 1240, bigger temperature, minus the initial temperature. It says the initial temperature is 27, so I'll write 300, because 27 plus 273 is 300 Kelvin. We need it in Kelvin. Plus, since the temperature changed, then there has to be a change in state. A change in state is 0.05 m times 105,000, because this is the latent heat of fusion, and they have given us in kilojoules, so we need to find it in joules. Plus, again, since, okay, first change in temperature, then there's a change in state, and then now that there has been a change in state, we need to bring it to now a change in temperature to match that of the gold. 0.05 m times 235 times, what's the final temperature? 1340. We have to match that of the gold, minus 1240. I hope it's not overwhelming. When it comes to gold, the gold is already melted, so we only have to deal with the change in temperature. But when it comes to silver, it's like, think of, there's a pot and then there's melted gold in there, and then you just pick up a cube of a silver and you put that in the pot. Now the silver is solid. The silver has to change its temperature. The temperature will increase, and then this increase in temperature is reflected by this, and then there will be a change in state where it starts melting to reach its melting point, and then the temperature will keep on increasing again so that it can match the temperature of the gold, because it says figure 2.2 to calculate the initial temperature of the pure gold so that the final mixture is the melting point of pure gold. So I have to reach when it reaches its melting point, I have to make sure that it reaches the final temperature is that of melting point of the pure gold. And I hope that makes sense. And now all you have to do is just put them together mathematically and you will be able to solve it. Let's do it together. I'll use this. I like this color. Okay. So 0.95 times 129, and I will have 122.55 m I minus 1340 equals, you solve this, first this, you get 11,045 m, plus you solve this, you get 5,250 m, plus You solve this, you get 1175 m. And now you just solve them mathematically, you get 1225.55 m I minus 164,217 m. And then when you add all of this, you get 17470 m. Now I can take m common in this. 1225, I hope my calculation is correct, minus 164,217 equals 17470 m. I cut this m. And okay, why did I write m here? Okay, wait, this is not m, this is I. And then 1225.55 I equals 17470 plus 164,217, and then you divide this 17470, you add this first, and then you divide this by 1225.55. And then the answer that you should be getting is around 1482.55, which you can write as 1483 Kelvin, and that is your answer. I hope all of this made sense. If you have any question, small or big, do not hesitate to comment it down, and I'll make sure to get back to you as soon as possible. Have a great day.